Hello everyone, I'm Dr. Jyoti Mandala. Welcome you all to the video lecture series on the course operating system. In this lecture, let us understand about deadlock prevention. In our last lecture, we understood about what is deadlock and what are all the deadlock characterizations are. We understood deadlock, if it is there, means there are four conditions which has to be occur simultaneously. And to check whether a system is in deadlock or not, we have a resource allocation graph, and we have multiple cases for that, and depending upon the condition, depending upon the case, we can say the system is in deadlock or not. In this lecture we will see how to prevent our system to enter into the deadlock state, because we all know prevention is better than cure. Once a system enters into a deadlock, it may be difficult to revert it back, right? So let us make our system way we will be preventing our system and to enter into the deadlock state. We all should ensure like your system should not be in a deadlock state, isn't it or not? Okay, now how can we prevent our system to enter into the deadlock state? The thing is here, all the designers who are all designing the operating system, they need to take necessary preventive steps at the development stage itself, so that the system should not lead to the deadlock. So at the time of developing the operating system itself, the developer has to ensure like this system should not lead to the deadlock state. Now how can we do that one? To do that one, let me quickly revise. In the last class, we have already understood the necessary characterizations of deadlock. Do you remember there are four characterizations for the deadlock? One is mutual exclusion, second one is hold and wait. These are all the deadlock characterizations. We have already learned in the last class in detail what are all these things. I hope you all could recollect that one. So these deadlock characterizations, whatever mentioned here, it says if these characters, if these conditions happen simultaneously, then the system may lead to a deadlock state. So we should ensure like these condition should not happen simultaneously, or these conditions should not happen. So if we could able to avoid these conditions, then we can prevent our system from entering into the deadlock. Now, how can we avoid these conditions? That means how can we ensure like these conditions are not happening? Okay, so we will see one by one. You already know what is mutual exclusion. In the last video, you have already understood in detail what is mutual exclusion. I'll quickly revise that one. Mutual exclusion is nothing but if we have resources, suppose if we have a resource R1, and if this resource R1, if it is being used by a process P1, then any other resource who wants to use this resource should wait. They are not allowed to use, because this resource is a shared resource and it can be used by only one process at a time. Now, why we are doing this kind of synchronization? Because we don't want to have inconsistent data, or it may lead to a race condition also, that we have learned in our previous videos. So to avoid that one, what we have made, all the shared resources whatever we have, those resources will be kept in a critical section, and if one process is using that resource, another process has to wait. One simple example is if you have a printer. Now if one process is using this printer, until and unless its work is done, another process has to wait. Why? Because if both the processes are using the printer, the our printouts what you are getting may not be in a particular order, in a perfect order, right? So if P1 got a chance to use the printer and if P2 wants to use this printer, it has to wait. This is called mutual exclusion, right? But if you want to avoid, this is one reason to may have happen the deadlock situation. But if we could able to avoid this mutual exclusion, that deadlock will not happen. But but practically we cannot remove this deadlock. It is impossible. Why? Because we want to eliminate that inconsistency of the data. So we will not remove this deadlock. So of all these four cases, we will not be thinking about removing this deadlock, that not deadlock. We will not be thinking about removing this mutual exclusion. Okay, so mutual exclusion is very much important to achieve this process synchronization. Right. So now our main concentration is how to avoid this hold and wait. Okay. Hold and wait, and how to avoid this no preemption, and how to avoid this circular wait. So we will not be considering this mutual exclusion as part of our deadlock prevention. Right. Now, okay. Now let us see how hold and wait can help us in achieving this one. In preventing, like how hold and wait can be removed so that we can prevent our system from entering into the deadlock. Okay. Keep heading all of you. Hold and wait. Now you all know hold and wait is nothing but if there is a process, okay, and that process what it does, it is holding one resource and it is requesting for another resource. The scenario is like this. Let us take one same old diagram, same old option like this. Let us consider this one where you have two processes and two resources, process P1 and P2 and process resource R1 and R2. Okay, now if you see this diagram, P1 is holding the resource R1. Understand this diagram how it is working. P1 is holding the resource R1 and then it is requesting for R2. This is called hold and wait. And similarly, P2 is holding R2 and requesting for resource R1. So because of this, P2 will never get R1 and P1 will never get R2, which will lead to deadlock. Never get means they cannot perform their task, so they cannot complete their task and it will lead to deadlock state. Right. So to avoid this hold and wait, they have suggested two approaches. The first approach is you need to eliminate this hold and wait. Always we need to try to eliminate this hold and wait. How can we eliminate? For that we have two approaches. The first approach is a process can request for another resource only when it is not holding another resource. That means in this scenario, P1 is requesting for resource R2. It can request for another resource if it is not holding any other resource. In this scenario, if you see P1 is holding R1, in that case, it cannot request for another resource. I hope you all got the point here. So any process can request for another resource only when it is not holding any other resource. I hope you all are clear. So in this case, what? P1 cannot request for resource R2 and also P2 cannot request for resource R1. Right. Okay. The second scenario it was given is the second approach it is given is a process should request all the resources at once. Suppose if P1 wants R1 and R2 both, then it should not grab R1 first and request for R2. It should not happen. What it has to do, if P1 requires R1 and R2 both, then it has to request for both the resources R1 and R2, and only after getting both the resources it can start the execution. It cannot take one resource and it cannot hold this resource and it cannot wait for the other resource. No. What they have to do, the process has to request all the resources at once, and if both are available, then only it can start the execution. I hope it is clear. So these two approaches are given to eliminate this hold and wait, but they are having some disadvantages. What are the disadvantages? Are poor utilization of resources. Why? Because here, even though R1 is available, because R2 is not available, it cannot use R1 resource. If it can use R1 resource, some part of the work can be done. But as per the assumption told, like if both are available, then only both can be assigned. Because of that, what happened, poor utilization of resources are happening. So poor utilization of resources. And second disadvantage is because the process is never able to complete. If the resources are not available, then the process may lead to starvation. If it is not able to complete and it is taking lifetime to complete its task, then we can say the process is in starvation state. So hold and wait can be removed by using these two assumptions, but still it may suffer from these two disadvantages. I hope you all are clear. Okay. Let us move to the next one. The next scenario is no preemption. Okay. So to understand this one, let us take the same example. But before that, all of you make a note. We will see the second one, third one, hold and wait. Sorry, no preemption. Okay, what is this no preemption is? You all might be aware, like until and unless the task is done by a process, until and unless a process completes its execution, it will not release its resources, isn't it or not? Let us take the same scenario. Let us take the same example here. Here, what happened? P1 got the resource R1 and it is waiting for the resource R2 so that it can complete its execution. Then if you see P1, it is holding the resource R1. It is holding the resource R1. P1 is holding the resource R1 and it is waiting for R2. Until and unless it gets R2, its execution cannot be completed. Once its execution is completed, then only it can release this R1. So because of that, the situation is like the system is going into a deadlock state. Now, in no preemption, how it can be eliminated is we should not have no preemption, we should have a preemption. Preemption is nothing but if the requested resource, in our case R2, is not available to be allotted to process, then forcibly this R1, which is held by P1, should be preempted, which should be released. I hope it is clear to you all. I'll repeat once again. If the requested resource P is holding R1 and requesting R2, if P is requesting for resource R2 which is not available, then whatever it is holding has to be forcibly taken out from the process. I hope you all are clear. So that is how we can eliminate this deadlock situation where we are converting no preemption to the preemption. Okay, let's move to the fourth one. The fourth one is circular weight. So keep your heading, all of you, circular weight. Now, what is the circular weight is? You all know this scenario. Do you remember this scenario where R1 is under the control of P1 and which is requesting for R2 and which is under the control of P2 and P2 is requesting for R1. Same diagram I have considered. Now this kind of weighting is called as a circular weight. Okay, so we need to avoid this circular weight so that we can prevent our system from deadlock. Now how can we eliminate this circular weight? We need to eliminate this. How can we eliminate this circular weight? Then OS is using here some mapping function. Okay, OS is using mapping function. What is this mapping function is? The mapping function is defined as F where R maps to N, where R is resources and N is an integer. What do you mean by that one? It makes one example I'll tell you. If you have one printer, okay, if you have one printer, then you can write printer is a resource and it is having n value 1. If you have two scanners, then you can write scanner is a resource and we have 2 car. Okay, now using this function, how we are eliminating the circular weight is there is a condition given. A process Pi holding a resource Ri, if a process Pi is holding a resource Ri and if it is requesting for Rj resource, then It can request only if it satisfies this condition. I'll write here, if a process Pi is holding a resource Ri and it is requesting for Rj. It can request for Rj only when this condition is satisfied. What is that condition? Function of Rj is greater than function of Ri. One example I'll take here. Example is, suppose process P1 needs the resources like R3, R6 and R4. Okay, then the following way of requesting the resources are allowed. What are the following ways? Like this. F of R4 is greater than F of R3. Right. So R4 resources can be requested after R3. Okay. Also, F of R6 is greater than F of R. Means R6 value is greater than R4 means we can request the resource R6 after R. I hope you all are clear with this one. So if the operating system is using this mapping function, then the circular weight can be eliminated. So in this way, we can eliminate the hold and wait, no preemption and circular weight so that we can prevent our system from entering into the deadlock state. Mutual exclusion can't be removed. I hope you all are clear with this today's topic of how deadlock can be prevented. Let us all meet in the next lecture. Until then, thank you all of you.